What's up everybody, today we are going to talk about backstepping reference tracking. We have talked about backstepping regulation problem in the previous videos. I am planning to put this video on a backstepping playlist. Hopefully you will see that. Okay, so let's go through some examples, and this is our problem. Okay, and what we want is to find a control law such that x1 signal, yes, the dynamics are stated here, x1 signal is going to converge, or rather we will also have reference signal. Okay, we will supply, and the error between x1 signal and reference going to 0 as t goes to infinity, meaning asymptotically. Okay, so we want to find this u control law, and compare to the regulation problem, this control law will not only depend on x1 rather states, and also it will also depend on reference signal. Okay, and in addition to that, like the derivatives of the reference signal, and maybe depending on the problem we will need to employ like second derivatives, third derivatives, etc. Okay, it depends on the problem. Okay, and so these are the dynamics. Okay, and here we want x1 to track the reference, so it would be better for us to write down the dynamics like in form of aerodynamics, and we are kind of familiar with that when we were looking at the, for example, observer. It can be nonlinear too, right? And observer design, we would always try to put the problem in a error dynamics form. Okay, and here this is kind of related to that idea. Here this is the error. Okay, and if you look at this we can explicitly write this expression as r dot minus x1 dot. And what is x1 dot? X1 dot is this. Okay, so explicitly we can write this down. Okay, of course we don't know at this stage, rather we don't know what r dot is, but at the end of the determination of the u, the control law, we will construct some type of reference signal, right? And it is probable that reference control law will require a couple of derivative terms regarding the reference signal, and yeah, we will also keep that information in mind. Okay, so back in the backstepping integration problem, we will write down x2 as phi1 plus z2, and why we are going to mention it now. So if we look at the dynamics and consider this problem as some type of regression problem, let's write this, and this is u input, and this is x3 dynamics. Okay, and x3 dynamics will produce x3 signal. Okay, the state, third state, and x3 signal will be the input to x2 dynamics. Okay, and x2 dynamics produces x2 signal, and this x2 signal will be the input of x1 dynamics, and it will produce x1 signal. Okay, this was the regulation problem. Okay, and if we recall, we would write down x2 in terms of, we will write down x2 as some type of error term. Okay, and a function of x1. Okay, so if this is the function of x1, right? I mean, it's probable that we would like x2 signal to be some function of x1. Of course, we are going to determine that function, right? And So this over x1 dynamics are asymptotically stable. Okay, this is the like general idea. Okay, but this is not regulation problem. There is also reference signal that we need to keep that in mind. So it is probable that the function or the signal that we want x2 to converge, okay, is also going to be depending on r, the reference signal. Okay, so it is really related to that backstepping regulation problem. All right, so if we derive that, if we take the derivative of this expression, we would have this term. Okay, and let's isolate z2 dot. Okay, we have this. Okay, and substituting x2 dot as x3. Why? Because of this expression. Okay, and this is our z2 dot term. What is z2 dot, or rather what is z2? Z2 is this. We want x2 to be like, of course I'm changing the idea between the reference tracking and also regulation, and I'm assuming you kind of know which one I'm referring to. Okay, we want x2 to quote unquote track the phi1 signal. Okay, but will it be the perfect tracking? No, we will also have some type of error signal, right? I mean, after the convergence, error might go down to 0, but in the transient, at the start of the operation, there will be some error. Okay, x2 will not be equal to phi1 signal, but there will be also error signal that we need to consider. Okay, and this z2 term is that term, error, between the x2 signal and also the signal that we want x2 to track. Okay, in a way, x2 reference tracking signal, x2 reference tracking error signal, z2 is. Okay, we can like consider in that way. Okay, so here we can write down the dynamics in this term. Notice we just switch x2 here, x2 as this express notation expression. All right, so I'm looking at this, I'm looking at my notes. Okay, and this is also the term, right? So okay, we just kind of transform the dynamics that we are interested in. Okay, so maybe let's go down. Okay, so these are the same dynamics, and again we are going to do the same like operation or thing for extreme. Okay, and again keep this little work diagram in mind. Okay, we will construct another function, let's call it phi2. Okay, and this phi2 will be a function of x1 and x2, rather the function of the terms that are like, if we look at this point, and there and the states whose dynamics are located at the right of this like point, we will include that. Okay, and we will include those states as the states that phi2 signal is depending on. Okay, so let's write it x1 comma x2. Okay, all right, so we want x3 to track this phi2 signal basically. Okay, and it goes back to this idea. Okay, what is that idea? We are going to construct some phi function so that this phi x2 function is going to like track that phi1 signal, and the overall dynamics will be x1 dot equals phi1. Okay, and other some x1 related terms. Okay, and and also z2. We will also have this error term. Okay, and we can consider this as like disturbance signal. But if this is kind of, I'm going to say this like important subject, and if this this whole dynamics is input to stay stable, then we will conclude that okay, x1 dynamics are stable. Okay, so this is all the general idea, and we will like step by step iterating this idea, and we will conclude, we will construct phi2 signal for x3, and also if we had other more, like if we had more dimension of, like higher dimension of dynamics, we will like iteratively employ this idea. Okay, so let's take this term. And also input to state stability is an important subject. I mean, I am aware of that. We in the previous video, like backstepping regulation problem, we kind of gloss over that. We, in a way, we assumed this signal like error term to be non-significant to a degree that we don't need to consider that, and we didn't consider that. And but it would be more like former approach to consider that, and to consider that the tool that we need to like learn, I haven't done any video about that, but I am planning to do that. We need to look at the subject of input state stability. Okay, and hopefully in the future, yeah, I will get down to that. All right, so we are here again, the same idea, like x3 will be written and in terms of, and since I had some type of space problems, I didn't want to include like x1 comma x2 comma r and also r derivatives of r term. Okay, and also some corresponding error term. All right, and if we take the derivative of that expression, we have this, and we can isolate z3 dot. Okay, we have that, and we can substitute this using this. Okay, and we have that expression that we can substitute in the dynamics, okay, set of dynamics equations. Okay, so it kind of looks like many random terms together, but there is some type of simplicity in that. Now we are going to look at this. Okay, so first of all, it is kind of annoying in a way that we are used to seeing like only one term at the left hand side of this like equations, and now we don't have that. And if you remember, that type of, I guess, structure also like manifests itself in observer design, right, subject. Okay, so these are the dynamics. Okay, and this is the Liopono function that we are going to like employ. So in a way, this can be considered as some type of control Liopono function. Okay, and this will be some type of like guideline for us to construct the input signals. Okay, and also the control law. So this Liopono function, first we are going to construct it as a like, the first requirement for a function to be a Liopono function is the positivity, right? Positive constraint, and we will just start from the generic Liopono function, I guess. Example, okay. This is the generic Liopono function, and we will start from that, and we are going to take the time derivative of that, and of course v dot must be negative definite, right? And using that v dot being negative definite, we will find a u such that this constraint is satisfied, basically. Okay, the general idea of finding control law using some type of reference or guideline Liopono function. Okay, all right. And here again, this is the generic Liopono function, and again there is some type of like decoupling going on, right? And this decoupling is the, I guess, result of the variable change that we have employed earlier. For example, you remember this block diagram, right? And in this block diagram, we write down x2 in terms of phi1, which is the function depending on x1, right? And we employed this variable change, and this variable change resulted in this Lyapunov function decoupling. Okay, and again we have this type of like special structure due to this variable change. Okay, here let's take the v dot. Okay, and I mean it may look messy. Okay, so bear with me for a minute. This is E1. If you want it, we can call it E1. Okay, and E1 square, and let's take the derivative. E1 dots E1 dot. Okay, E1 times E1 dot. Okay, and this is the same idea basically. Here this is E1, right, and this is E1 dots. And let's look at the dynamics. Here we will write this expression that place. Okay, so basically this is E1 and this is E1 dot. Okay, and here this is Z2 and this is Z2 dot. Okay, and we have this Z2 dot expression from the dynamics. Okay, and this is Z3 and this is Z3 dot, and here this is Z3 dot. Okay, and we want this to be negative. Okay, and here we can see our U term, and so far we haven't constructed what phi1 and phi2 functions are, and we are going to the structures of the phi1 and phi2 will appear in the manipulations down below. Okay, they will like present themselves, their structure will appear, right? And it will be clear what to use for phi1 and also phi2. Okay, and we will start finding what phi1 should be, and then after that, like iteratively, we will find phi2, and phi2 is probable that phi2 will be depending on phi1 dot and also phi1. Okay, so let's continue here, and this is Z2 term and this is Z3 term. Okay, and we don't want to have any Z2 and Z3 term in this parenthesis. Okay, so by using this and also this, right, by using this term we can get this term, and we can get Z2 times something terms to this into this bracket. Okay, and in addition to that we don't want any Z3 related term in this bracket, so we can get the Z3 times something terms into that bracket. Okay, and here this is going to go here, and also since we have Z2 Z3, and this is going to go to here. Okay, same idea that we considered in the backstepping regulation problem. So here this is the part that we need to look at right now, and this term. Okay, this term, and also this term, and finally this term. Okay, so we are going to start from this like first term, and this term, this is E1. Okay, so we want this term to be like, for example, if this term, for example, were to be like minus E1, okay, this is E1 and this is minus E1, it will result in minus E1 squared. Okay, and also if this term were to be and minus z2, and since we have z2 here, this whole expression will result in minus z2 squared. Okay, and also the same idea, we want this term to be like minus z3 because of that same reason, and this whole like expression, bilinear expression, will result in minus z3 squared. And finally, it will be guaranteed that this the v dot expression is being like negative definite, okay, which is what we want. Okay, so basically we want this term, again to reiterate, we want this term to be minus e1. Okay, all right, minus e1. I'm referring this expression as e1. Okay, and we can isolate phi1. So phi1, and phi1 is again function of x1, r, and r dot. Okay, which is, we expected that, right? Okay, so here if we look at this expression, maybe I should like clean this a bit. If we look at this expression, we want this term to be minus z2. Okay, so this term result in minus z2 squared. Okay, the same idea. All right, so here this term should be minus z2. Okay, in addition to that, of course, you can, I mean, this is a choice, right? This is some type of like design choice. You could also choose, I guess, minus z2 cube. Okay, so this two expressions will result in minus z4 to the 4, okay, instead of minus z2 squared. Okay, I mean, they both are negative definite. Okay, so there is no problem with that. Okay, and we can isolate phi2 here. Again, phi2 is depending on phi1 dot, or rather phi1, and also x1, r, and also z2. Okay, we will, again, don't forget z2 is, let's go up, and z2 can be written as like x2 minus phi1. Okay, so z2 can also be written in terms of like state variables. Okay, so here finally this term must be, or we can choose this term to be minus z3. Okay, minus z3 here, and we will isolate u and this term. Okay, that's great. So we are basically done. We are basically done at this point. What we want to find is to write down the explicitly phi1 dot, phi2, and phi2 dot, and also u. All right, explicitly. When I say explicit, I mean like in terms of state variables. Okay, so this is the finer, I guess, term that we need to look at, and again we need to find like phi1 dot, phi2 dot. I mean, we already have what phi1 and phi2, right, are, and we will obtain phi1 dot and phi2 dot, and also u, control law, and in terms of state and reference signals. Okay, all right, so of course this type of operation will be very laborious, and it would be suggested to use MATLAB symbolic or any type of symbolic manipulation capable software. Okay, and here we can basically define as symbolic variables. Here we can say x1, x2, x3, and u. Okay, and also type in real. Sometimes it would, sometimes MATLAB can consider them as like complex variables, right? And it will make things easier to also assume, or make MATLAB to assume, hey, these are real variables, so don't think about them as complex ones, okay, because then you would see, depending on the operations that you do, you will see, well, like conjugations, etc. type of expressions in your calculations, okay. And here we can see r dot, r double dot, r triple dot, okay. And we can also define phi1, phi2, and z2, z3, okay. And we also stated in terms of, or those signals being functions of t, so this will come in handy, okay. There is a reason why we do that, and it's important, okay. Here these are the dynamics, and this is phi1. Here let's look at that, this expression and this expression, they are same, okay. And we basically written that down, okay. And what we want to find is phi1 dot, okay. And if we write that down, we will see this term, okay, this term. Why? Because phi1 has r signal in it, and if we differentiated it, and also if we also defined that type of expression where r is a function of t, right? So it will generate that, okay, basically. And but we want to have a more concise expression, so we additionally, right, additionally we also define r dots, and just substitute whenever you have this expression, substitute r dots, okay. And the same idea can be applied for derivative of r dot with respect to t, okay. That's why we defined r dot and also r dot maybe, okay. And here we will also have x1 dot. Why? Because phi1 is a function of x1. So if we take the time derivative of phi1, we will also have, and since x1 is a function of t, right, we will also have x1 dot term, okay. This is like no-brainer, okay. And we can also write this in expanded form, so we don't have any like factorized structure, okay. All right, so here now we are done with phi1 dot generation, and we have phi2. Here let's look at what phi2 is. Phi2 is phi1 dots and some other terms. Here we can see phi1 dots, right? And we have z2, and z2 can be written as, we talk about this, like in terms of state expressions, okay. That's why we, at the start of the phi2 and also phi2 dot generation, we wanted to make things like easier, so we immediately change z2 in terms of the state variables that we are we know explicitly what they are, okay. And we want the final expression to be only depending on state variables and also reference signals, okay. So we don't want to have a control law where there is z1 or z2 etc in it, which is not, I mean, they are not state variables, okay. We can, yeah, okay, that's, I don't think more explanation is necessary. So we are basically creating phi2 dots, and phi2 dot of course will have like many derivative terms in it, okay. Why? Because phi2 signal has phi1 dot in it and also r x1 and z2, and so we will also have r dots as a result of this differentiation operation, okay. And to make things easier, okay, MATLAB is going to generate this, and we want this r dot like term to be substituted for this longer expression, so the final product can be written in a shorter, right, okay, expression. And we can see r double dot and also r triple dot, and also this is x1 dot expression, and this is x2 dot expression. Okay, and we can also expand the resulting term, is phi2 dot, and this is the control law. Let's look at this. Minus z2 minus z3 and y2 dot. Okay, we are basically writing that down, and we can substitute expression form for z2 and for z2. Okay, and also we can do the same thing for z3. Okay, we know what z2 and z3 are in terms of set variables. Okay, so this is the final like result, the control that we need to employ. Okay, so let's go down, and this is MATLAB Simulink simulation, and I'm looking at my screen to see if you are able to see that, if the expressions appear clearly. They are not perfectly clear, but okay, they're, but you can see like generally, and I will like explain all of them one by one. We have 1, 2, 3, and let's call it 4. Okay, we have 4 like sub blocks, and we will talk about them. Okay, so this is, I think it is obvious what this is. So if you look at the control law, we will have r triple dot in it, right? And so not MATLAB, but also not many like softwares and numerical simulation softwares, they are not easy, or they don't like to deal with taking derivative. Basically, if you can get away with taking integral instead of taking derivative, do that. Okay, and so we are basically doing that, and we don't want to generate some reference signal and to have r dot, r double dot, and r triple dot terms. To have those terms, we don't want to use like derivative blocks that Simulink has, and because that would result in very interesting numerical problems. Okay, MATLAB would, and also Simulink would have a hard time dealing with it, and even for small scale problems, it will not be able to like deal with that. It will throw many types of errors. Okay, like unstability type of errors. Okay, so since reference signal is something that we like produce, right, generate, it would be better just to generate our triple dot and then take the integral. So if we take the integral of our triple dot, we will have like r double dot, and also again we can take the integral again, right, and we will have r dot, and also one more time, and integration, and we will have reference signal. Okay, so this is something that MATLAB is totally capable of dealing with, that because there's no derivative terms, and derivative terms are annoying, say the least, right? Okay, so let's look at the second block diagram. Okay, here this is basically control law, control like U signal generation, and if we remember when we were dealing with the computational manipulations to explicitly write down control law, okay, and we had U depending on like state signals and also reference signals, basically. Okay, so this block basically generates input signal, and okay, so here this is the inside of it is given here, and we just written that down, the control law that we generated using symbolic toolbox. Okay, this is the same like expression, so let's keep this in mind. So let's go back and look at that. Okay, here, same expression, the result of this whole like symbolic manipulations. Okay, and okay, so let's look at the third block, and this is basically type of system, right? And here we can see states and also input like provided, and exat being generated, and exat like we need to take the integral of it to generate x, right? And we have x1, x2, x3, right? We use this go to like little blocks to deal with some type of signal routing, okay? And so the resulting block diagrams and simulating, I guess, Fordle would look easier on the eye at least. Okay, so this is something that this type of like simulation blocks is something that we are aware of, okay, we are familiar with. And this is basically reference signal and x1, and this is the reference tracking error, okay? And we will look at what it is. If we see that error signal to be, converging to 0, that means okay, everything is in order. And we can also see reference and x1 signals, okay? So we can also look at them like in the same plot. And here this is like x dot equals f of x comma u type of block, and in that block we written that down. And if you recall, this is the like dynamical system expression, and these are the dynamics. So okay, nothing new for us. And here this is the final like result, reference tracking, I name it. And this red signal is, by the way, I started here, you need to specify your initial conditions, and I started x1, x2, x3. I started all of them from 1, okay? So this is initial conditions basically, okay? So this is real x1 signal, and this is black one is the reference signal. So it starts from that and it converges to the reference signal, okay? So this is the basic idea, and how to use backstepping control to control and also for reference tracking applications. Okay, and this is it, and thanks for watching.